Good morning, everybody, and welcome back to Next Door NetAdmin. Today, I'm going to talk a little bit about some of the foundational electronics that power a computer, or in this case, a server. The goal here is to end up talking about some of the modern electronics that kind of help power a server that are not necessarily common knowledge. But I want to talk about some of the foundational stuff before we get there. So here we go. When you first turn on a server, some of the first code it loads, obviously, is from the BIOS. It includes the instructions on how to test the various pieces of hardware, how to detect them, how to configure them, all of that stuff. Where's the BIOS, or UEFI, stored? In the BIOS flash, right? Okay. How did we get to having this flash storage? And how is it similar to or different from the common flash memory that we now have for like SSDs? Is it the same thing? Or is it different? Spoiler, it's a little different. So let's figure out how we got here. Originally, this was just ROM, read-only memory. There was a very basic operating program that was essentially burned into a piece of silicon. When they actually did the imaging of it, the lithography is what I'm looking for, it would actually create a hard code set of transistors, resistors, everything that was linked into a particular pattern that encoded the operating instructions for the ROM. So that, okay, when you turn on the machine, it just loads the instructions from ROM and starts executing them from the very beginning. Easy, simple, but not especially upgradable. And in fact, you would end up with machines that had a ROM socket on the motherboard. And you had this on some routers too, because Cisco routers had the same idea. You could actually upgrade the boot ROM by pulling one chip out and replacing it with an updated version of the ROM. Cool. Well, that works. But it's not especially convenient, is it? Because anytime you have a new ROM program, you have to go out, create the actual physical chip. Then you have to convince people to buy that chip. And then they need to go through and have the specialized, tools to pull the chip out of the socket, because it's not like it had a handy lever or anything like a CPU. They had to pull that and then put the new ROM in and really hope that they didn't break anything while they were at it in order to do an upgrade like that. So for many reasons, that was the starting point. Okay. And also, the fact that you have to do lithography to do this, you're actually burning it into the silicon, is not particularly convenient, because you have to create new image and then you have to put it into a fab and everything else. So for a lot of reasons, that's a major hassle. Then we moved forward to programmable read-only memory, or PROM. A PROM was, essentially you could create a whole bunch of these blanks. And then electrically, you could program it. There are still versions of this out there today. Let's talk about the Nintendo Switch. The Nintendo Switch actually has fuses, hardware fuses. They start in one state, but if you send a little bit of current through them, you can confirm that the fuse is still intact. If you send a large amount of current through them, they blow out. They actually physically melt. Just a little poof, and they're gone. The switch uses this as a form of anti-rollback when it does firmware updates. When you install version, I don't know, I'm going to pull a random number out of thin air, version 8.6 of the firmware, it checks and it says, okay, I'm supposed to have 14 fuses on this. Oh, I'm on a motherboard that has 15 fuses. All right, then I'm going to short one out. Bang. Okay, now you're at 14, which is what it's supposed to be. If you try and roll 8.6 back to, I don't know, 8.2, 8.2 says, I'm supposed to have 15 fuses. I only have 4. Excuse me, I only have 14 fuses instead of 15 fuses. So that means I've already been updated and somebody's trying to roll me back to something that had a security hole or whatever, so I'm going to refuse to run. So that you can go forward as many versions as you want, and the new version of firmware will short out those fuses until it gets down to the number that it should have, and then you can't roll it back. PROMs work kind of like that, in that it's a blank template with all of the connections there, and then electrically you can short the connections that you want to short, so that you wind up with a chip that has all the zeros and ones, the equivalents, and all of the connections that you want to form your ROM program. But it's a one-time operation, because you're going from a blank to something that's programmed, and once it's out of that programming station, which has the higher voltages, you can take that, plug that into a motherboard socket, and it's only using the lower voltages to read it rather than the higher voltages to program it. And that's a one-time thing, because you can essentially blow all the connections and then it won't work at all, which is kind of pointless. But there's no way to restore those connections once you have blown them. So it's a one-time operation. Programmable, read-only memory. All right? Then we moved forward to EPROM. Only one E. If you know anything about the electronics, this is the one E for EPROM, which was erasable, programmable, read-only memory. This used a different setup, and I'm not going to get into the physics of how this architecture actually works. That's something that's better suited for a hardware engineer to discuss, and that's not me. But essentially, you can program these chips by shoving, a charge into a floating gate. And the erasable part comes from ultraviolet light, or you can use X-rays as well, but the light can actually knock the charge out of where it was stored. And so ultraviolet light can erase the chip. Some of them would have just a quartz window in the top of the chip. Then you can expose it to strong ultraviolet light and it'll erase. You could also essentially expose it to a day, like a full 24 hours worth of sunlight. That has enough ultraviolet radiation to erase the chip as well. If you left it exposed underneath standard fluorescent tube lighting, that will also erase it given enough time. I think what I was reading says about 3 weeks worth. Could have been 3 days, but I think it was 3 weeks. Because that also puts out a little bit of ultraviolet light. So over time, leaving it exposed underneath fluorescent tube lighting would also erase the chip. But there were a lot of these that are just encased in solid plastics that no ultraviolet light can get to them. Technically, they're still EPROMs. They could be erased, but they're essentially one-time programmed, because then they're encased in plastic and they're not supposed to be erased after that. Okay, I do not have any evidence for this, but to me it makes sense that this is where we would get the first iteration of flash memory. Because to erase the chip before reprogramming it, you're going to expose it to a brief, high-intensity burst of ultraviolet light. Maybe not so brief, but essentially, compared to the lifespan of the computer, it would be brief. But then you could use the programming station to reprogram this. Okay. The next stage in this technology would be EEPROM, and that is two E's. We went from ROM to PROM to EPROM to EEPROM, EEPROM, which is electrically erasable, programmable, read-only memory. See how we're building this up one letter at a time. Electrically erasable PROMs do the same sort of programming by shoving a bunch of electrons into a floating gate that produces a charge, enough so that when you run a bit of current underneath the floating gate, you can detect whether there's a charge there or not. That forms your 0 or your 1. But if you use a slightly higher voltage, you're relying on a tunneling effect, and I don't remember the exact name for it. Again, if you want more details on the physics, go find a hardware engineer and talk to them, because it's fascinating. It really is. It's just not my area of expertise. But if you put it through at a higher voltage or a higher current, one of those, essentially these stored electrons do some, quantum tunneling down out of the floating gate, and it discharges. EEPROM forms what we would understand today as the basic kind of BIOS storage, because it can be electrically erased and then reprogrammed essentially at will, which of course has its own security issues associated with it, and that's why these interfaces are typically not something that the computer does on a regular basis. It actually requires specific command channels and specific access in order to be able to do it. Sometimes that can be done from within an operating system, sometimes it can't, so your mileage may vary depending on what the manufacturer of that particular BIOS chip has decided to make available. But the general process is the same, with a little difference. In modern usage, EEPROMs are notable mainly for the fact that you can do your erasure and reprogramming down to the bit level sometimes. You can individually erase 1 bit or 2 bits or however many bits you want and reprogram those, and it requires 1 transistor per bit of data to be able to do that. This is different from modern flash memory, which works in pages, and it's 1 transistor per page of memory, which is also why flash drives, whether they're on USB or in regular SSD, they work in pages. You can program them individually, but if you want to erase anything, you have to erase the entire section. Which is also why, essentially, if you're deleting a small file, what the computer actually has to do behind the background is say, okay, well, let's take a brief snapshot of what was there, erase the entire page on the drive, and then reprogram it with the data that was there minus the data that was deleted. And there's a whole bunch of other commands that have been introduced to try and figure out ways of dealing with this without accumulating more write cycles, essentially. By deleting data, you don't want to have to erase and then write and erase and write every single time. That rapidly degrades the lifetime of the memory cell. So in modern flash, there are many ways of dealing with this, but it's not usually on the individual bit level like true EEPROM is. And yet EEPROM forms the basis for these kinds of electrically erasable and reprogrammable read-only memory, or in the case of BIOS, flash memory. And nowadays, flash is not literally an ultraviolet pulse of light to erase the cell. It is talking about, how fast the memory is. Or it's talking about how it's just a quick little burst of electricity that just flashes through the chip. Or you can use it to say, I'm flashing a new version of the software, which is, essentially reprogramming it. You erase it first, and then you reprogram it electrically. So it can mean many things now. But I still think, and I say this with no authority whatsoever, but I still think it's all related back to how you can actually erase the original EPROMs with ultraviolet light. It makes sense to me. I don't know if it's true, but it makes sense to me. And once you have EEPROMs that are electrically erasable, and you move into modern flash, there's a relationship between how easy these are to program and their longevity. If you think about it, one of those original ROMs that were created through lithography, they're basically there forever because it's literally burned into the hardware. If you think about PROMs, yeah, it's also pretty much there forever because the programming has created actual alterations in the hardware itself. And yes, you could essentially erase the whole thing by blowing all the fuses. But as long as you're not using the higher voltages and you're using just the reading voltage, then you can essentially read that forever. An EEPROM, where you need ultraviolet light to erase it, is very, very stable. It's not uncommon to have something that's lasted for 25 years or more, and it's fine. EEPROMs, the electrically erasable ones, every time you erase it, you're weakening it. That's just how it works, because you have to shove electrons up into a floating gate, and then you have to pull them back out. Well, every time you're pushing and pulling them across that boundary, the boundary wears out. And so it won't hold the electrons up there as a static charge. They'll leak down over time. And so whatever you stored in it, whether it's a program or whether it's data, it will eventually leak out. That's why standard flash memory grows more unreliable over time. It's because the number of times you erase it and rewrite it, you're weakening that boundary. And that's just a fact of how the technology works. So the more difficult it is to erase and reuse, the longer it will be good for. And as you start making it easier to erase and rewrite it, well, that also means it's not going to last as long. That's just the price we pay. So, yes, if you find older technology that's using an EEPROM or a PROM or even just an actual ROM chip, you can expect that's going to be good for a long, long, long time. And in the case of an actual physical ROM chip, probably basically forever, as long as you're going to be using it anyway. But when you're looking at EEPROMs, they'll be a little less, they'll have less longevity in operation. They'll still have a lot of uses. They'll last for a while, particularly if you're looking at what the industry today refers to as EEPROMs, which has an individual transistor per bit, and they're small storage, sometimes just a few bytes, sometimes a few kilobytes. But when you look at the bigger chips, like a 16 megabyte chip, you're probably looking at something that is erasing smaller pages, but pages of memory at a time, and then reprogramming it. That will last a little less long. And if you're looking at the, massive gigabytes of flash memory that you have in SSDs, and whether that's on a phone or whether that's on a 2.5-inch drive or if it's on an M.2 drive, that kind of flash memory, which is essentially made to be erased and rewritten a whole bunch of times over its lifetime. That's why they only have a lifetime of like 5 years, maybe 10 years if you're really good to them. Is because they're made to be more easily erased in bulk and then rewritten. So that's some of the interesting fundamental foundational electronics. And when you look at that, you can say, okay, so I've got different classes of storage for this, but where you use them, and there are other technologies that can be similar in a different way. That's what I'm going to talk about next time. We're going to talk about some of the really interesting things that you can find in the server world that might look like a bunch of acronyms to start, but they can actually be really interesting things when you look at them. So something to look forward to for next week. Hopefully you found this little discussion on the foundations of it interesting, enlightening. And yes, that is a kind of an intentional pun this time, seeing as we were talking about flashing with ultraviolet light and everything, but yay, puns. If you have thoughts on other things that you would like to hear me talk about or things that you would like to see me demonstrate, feel free to let me know right down there in the comments section. Otherwise, thank you very much for watching. I am your next door netadmin, and we will see you next time.